All right, so welcome back to the Civil FE exam review. Um, Today in this video, we're going to be continuing our dynamics review, and we're going to be looking specifically at work, energy, and power. So if you haven't checked out any of the videos prior, right, ones like force acceleration, mass moment of inertia, or kinematics, for the dynamics review, make sure you check those out and master those as well. All right, so let's look at this practice problem. Number 1 says a rubber band is stretched by 0.2 meters. If the force constant is 100 newtons per meter, calculate the elastic potential energy stored in the rubber band. So what information are we given? Well, we're definitely given the distance stretched, right? Which is going to be your 0.2 meters. You're also given your constant force. Or the force constant, which is 100 newtons per meter. All right, we're trying to find the elastic potential energy. So find elastic potential energy. All right, what are the formulas that we need? Well, I know we need to probably be searching or looking at potential. I'm going to be wanting to look at potential energy. So I'm going to do a search in my handbook, my reference handbook, and do potential energy. Something came up. All right. So not this section. All right, so it's important to note that potential energy is denoted by Ti or T, and potential energy is denoted by V. So just something important to note. All right. So we got potential energy is equal to the elastic. So V is the symbol for potential energy. You got Vg, which is the potential energy in the gravitational field. And then you have Vee, which is here, denoted by the elastic potential energy. Okay. So I know that I will need Ve I know my formula is going to be Ve is equal to 1/2 Ks squared. All right, what is K? K is a constant. K is the constant. And it's the force in the spring. So it says a spring constant, K. So we're going to say our K is going to be our rubber band constant, which is 100 newtons per meter, right? Okay. And then what is S? Well, S for a spring, so it's a little different for a rubber band, but the force, okay, so the S is the change in length of the spring. So for us, our S will be the change in length for our rubber band. Okay, so S is equal to, and our change in length for the rubber band is stretch 0.2 meters. All right, so your potential energy is a little different for a rubber band versus a spring, but similar concepts. K is your force constant, and then S is going to be the distance that it is stretched. Okay, so we have VE is equal to 1/2 times my 100 newtons per meter times my S squared, or 0.2 meters. And I get this all to equal 2 joules. All right. So really, my units, it doesn't come out as joules, right? It comes out, my units actually come out first and foremost to be put it in my calculator really quick. 0.5 times 100 times 0.2. Yeah, so I get 2, but your units are going to be newtons, right? And then I'm doing meters squared over meters, so that's going to be Newton meters. So how do I get that to, how did I come up with, how do I get my final answer to be in joules? Well, let's look up. You can go into your handbook, go to the section where you're looking at your unit conversions. So unit conversions, and then within this, right, we have, see if we can find joules. Okay, so we know that, scroll over here, 1 joule equals 1 Newton meter. So we wanted to do our unit conversions. 1 Newton meter is equal to 1 joule, and therefore this is equal to 2 joules. Okay, so for my answer, I get B. Alrighty. Let's look at number 2. So it says if the kinetic energy of an object is 400 joules and its mass is 20 kilograms, what is its velocity? All right, so we're given the kinetic energy, right? We are also given mass. Anything else? No. What are we looking for? Or we're trying to find the velocity. And it needs to be in meters per second. Okay. What formulas might we need? So I'm going to do a search. I'm just going to do kinetic. Kinetic energy. Do a quick little Search here. Okay. So for a particle or an object, T is equal to 1/2 mv squared for kinetic energy. All right, so I'm given T, which is kinetic energy. I'm also given mass, and the only other variable that's left in this equation is velocity, which I can solve for. So I know this is the equation that I would need to use right up top. So T is equal to 1/2 mv squared. M is equal to 20 kg. T is equal to 400 joules. Okay. And if I know that 1 joule, right? 1 joule is equal to 1 Newton meter. Don't know if that helps me much here, but if I say 400 Newton meters, I'm just trying to make sure my units are able to cancel here. Is equal to 1/2 times 20 kg times v squared. All right, so once I solve, v is going to equal to the square root of 2 times 400, all divided by 20. And so when I solve for that, v is going to ultimately cancel out to be 6.3 meters per second. All right. So my answer is A. All right, let's look at number 3. All right. So this one says, Daniel is pulling on a rope to drag his backpack to school across the ice. He pulls upwards and rightwards with a force of 22.9 newtons at an angle of 35 degrees above the horizontal. So if I just draw that, because it's a lot to kind of unpack. It's like Daniel's pulling this way, right? Here's just draw my X and Y axis, right? So he's pulling upwards and rightwards with a force of 22.9 newtons. So I know that this angle is 35 degrees. And I also know that this is 22.9 newtons. All right, hopefully that makes sense visually. All right. And this is all to drag a backpack a horizontal distance of 129 newtons or meters to the right. Determine the work done upon backpack. All right. So what information are we? We're given a lot of information, right? We're given some force. The force at an angle, right? We're given the horizontal distance that's moved. What else are we given? That's pretty much it. And then we're trying to find the work done on the backpack. Okay, so being that we know, I also want to draw out where this backpack ends up. So from here, we'll just say to here is 129 meters. And this is where the backpack lands. Make it purple. Call this the backpack. Should it have some straps or something? That's a horrible backpack. But that's the backpack. We will color it in. I think that's making it worse. But just imagine you moved your backpack horizontally by pulling a rope, right? Across ice. That's also important. So they also let us know there's ice, so there's no friction force that's occurring on this. So they want to know the work done in joules. So the first thing that we need to know is what exactly is work, right? Work. We're doing work now. We're working hard. All right, so the work done. I don't think that really helps us. All right, there's 209. Okay. Different things, but work U is defined as force times a change in distance. All right, so that's really what you need to know for this. So a little bit of prior knowledge that you'll be using too, but mainly work is equal to force times distance. So we'll say U, which is work, is equal to the force times the dr, which is change in distance. Okay. So what is our change in distance? So just start substituting the variables that we're given. So dr, our change in distance, is equal to 129 meters, right? Okay. But that's in a horizontal, right? What is my force? Well, is my force 22.9 newtons? If you answer yes, you are incorrect. Our force needs to be in the direction that our distance changed in. So we need the force of x, right? Force in the x direction. We moved horizontally to the right in the x direction, so we need the force in the x direction. They give us force, right? Total force, 22.9 newtons. How do I get the force in the x direction? Well, I'm going to do cosine of 35 degrees. And that's going to give me my force in the x direction. So that comes out, once I put that in my calculator, I get 18.75 newtons. Okay. All right. So then work equals U, which equals force, which is 18.75 newtons, times a distance of 129 meters. Okay. All right. So that in turn turns out to 2419 Newton meters. We also know that 2419, we also know that Newton meter, a Newton times a meter, 1 Newton times a meter equal to 1 joule, right? So these units will cancel and we'll get 2,419 joules, which equals D. All right. So that concludes the dynamics section of the Civil FE exam review. The next section, we're going to be looking at, I believe it is mechanics of materials. Just make sure. But yeah, went through dynamics. We're going to be looking at mechanics of materials, starting with shear and moment diagrams. So we have gotten through 5 of 14 topics. So we're going to keep continuing to work hard and master each of the topics. I'll see you in the next video.